I'm happy to be here again today with Haris. And Haris is a computer scientist, and he's done work in fuzzy cognitive mapping. He has a special interest in group theory, especially the monster group. And we talked about that in our last episode together. And Haris brought up his theory about why the monster group exists. And I'm very interested in learning more about it. We had a few technical problems last time with some of the graphics, and I think you have fixed that. So maybe we can give it another go. And you had mentioned at the end of the last time that we talked that you think that this theory is one of those truth eternal theories, and that it has actually a spillover effect in other areas. So I'm hoping you can talk about those things as you go through the theory again.
Okay, that will be great. Okay, so hello everyone. It's a pleasure to be again at the MIDI code, and hopefully this time I will be a little bit more clear regarding the connection of the monster group and why it exists. That I believe it exists because of the prime values, let's say, and not exactly the primal values, but the prime m values, and that is those values that they are the pointers to the primes as we know it, let's say. So without further ado, allow me to show some of the things that I had prepared. Okay, great. Can I share screen?
Oh, sure. Sorry about that.
No worries.
There you go.
Sorry. Okay, perfect. Great. Okay, so just to show a bit, as I told you before, the order of the monster group, that is one of the 26 sporadic groups, simple finite groups, that they are the exception to the classification theorem in group theory. The monster is the biggest one of the bunch. It's so big that it actually includes 20 out of the 26 groups within itself, including itself. So the full order of the monster is very big. It's that number 808, and it goes on. What I am focusing here, I'm doing an initial, let's say, reduction, which is appropriate in this sense for our construction. And we're focusing on the minimal order of the monster group. And that is comprised only by the 15 super singular prime terms. So instead of having 2 to the power of 46, we just have 2. And in total, there are 15 terms. It's important to note the size, that is 15, and also the highest term. The highest term, it's this one over here, it's 71. So one idea is to start, as I told you the last time, the big breakthrough that I had was like the order of the scientific method can be changed, and it can be a higher synthesis followed by an analysis of that higher synthesis, and finally a total integration. And I will elaborate a bit now. So what we know actually is that the total number of the singular prime terms is 15. Half of that it's 7, and this becomes important in a few bits. But just to give you a small, how do you say, a small sneak peek into the algorithm and how many steps it will take. Actually, this can be calculated quite easily, and it's the size, that is 15, plus 2. We heard sometimes that it's important to have like the fine distinction, let's say. So I put that from the start. Now,
okay, I have a question to ask here. So
please.
Some people said in the comments that they wanted us to bring it down to their level. So since that would be my level, I'll have you bring it down to my level. So you said the total number of super singular prime terms is 15. Thus, as though this is obvious, thus the floor is the size divided by 2. Why do you get to make that move?
No, I just put it here because I said, let's say, imagine the following thing, because what we are doing here, what we are trying to do, especially the most important step is the first step, the step of the higher synthesis. That is, we apply a primality sieve onto the sequence that is A that we mentioned the other time. It is found in OAs and is A002822. So imagine that we are emulating basically now a total Turing machine. So not only a Turing machine, but a total Turing machine. And what is the difference? The difference is that a total Turing machine, as opposed to the simple one, it's always behaving well. And what does that mean? It means that when it accepts an input, let's say you give to the machine an input, it will go back and check if that input correctly can be accepted, let's say. And if that is the case, in our case does that input belong to the prime? Is it a super singular prime belonging to the master or not? If it's true, then it will accept it and continue to the next input state. But in case it is not part of the master group, let's say it's not a super singular number, it will behave well and reject it. So in terms of computer science, let's say our total Turing machine will hold and will be able to take out the tape, let's say. And because my assumption here is that because the initial size of our sequence that we would like to reconstruct, because it's one of the things that we know, it's not something hidden, let's say, the master, as we said the previous time, exists. So the size is 15, and now we're gonna, in this first step, we're gonna expect to get out of it this tape. And this tape is gonna be the floor of, let's say, half of the size. So we expect that to be 7. And just to start, what I'm saying here is it goes like this. So this is the first step. The first step actually has to do with getting the first number. The first prime number is 2. And it accepts it, of course, because it belongs to the master. So it continues to the next step. The next prime value coming out of that sequence is 3. Once again, it accepts it because it belongs there. And it continues up to the point.
So just for everybody who's watching who might not be able to see your cursor moving around, you're going from this column to this column, or from this row to this row to this row. So step 2, and then you go to M2, which is the next prime number, and then that comes down here, and the 3 is the next prime number in.
Yes, and then it's 5, then it's 7, then it's 17. As you see here, what we have done, we have skipped some numbers. Okay, this will be important later, because in the natural order of primes, after 7, we have 11 and 13.
Mm-hmm.
Okay, so here we skip that. Our sieve does not, our higher sieve, let's say, does not take that, but that's okay, that's fine. It is actually helpful, and I believe that is the correct step. So the next one that comes out of that sequence is prime 17. The sixth one is 23, and the last one is 47. The next one, the number 8, let's say, it's gonna be 103. But because 103 is greater than our, let's say, largest super singular term of the master, our well-behaving total Turing machine stops, and it holds and it prints out this tape. And when we calculate the size of the tape, let's say, when expected, we're gonna see that we have there 7 different values. Okay, this is why I make this distinction here, that 7 actually is the floor of the half of the size. Okay, it's just a small metric that I'm using. Now, this is as I told you, it completes the whole thing and of synthesis. And now what we have to do, what we can do is to go and perform the analysis of what? Of again, half of this tape. And what do I mean half? Imagine that we have this printed, okay, it has 7 different A4 sheets, for example, and then we fold it. When we fold it on half, where the fold is going to take place is going to take place right here, between 7 and 17, between M4 and M5, let's say. So again, this is something that signifies that what I am saying, that this symmetry breaking, as it broke right here after 47, it seems that it also there is another break exactly here. But let's start from analyzing these first prime M values that we got from our M tape, and we will see that the M1 value actually leads to a prime that is Q and a prime that is P. And the difference between them is always the same, is always 2. So how we can understand this basically is 6 times 2 minus 1 is 11, 6 times 2 plus 1 is 13. So we place down, since we re-emulated, let's say, the size of the initial tape, we can place down these 2 values here. And when you multiply these 2, you actually get the N value, which is 143 in this case. So we have Q, we have P, Q1, we have P1, and then we can move to the analysis of the next M value, which is M2. We get, again, 6 times 2 minus 1 is 17, 6 times 2 plus 1 is 19, and the N value is 323, which is 17 times 19. We continue as we have more space here to the third value. We take 5, and it's 6 times 5 minus 1 is 29. 6 times 5 minus plus 1, sorry, is 31. What is the product? It's 899. So this is our N3. Here it is, N3. So at this point, we notice that we still have one place left here. And this place corresponds to the fourth M value, which is 7. So we can note down the Q value here, which is in this case is N4 minus divided by P4, or just Q4. And what is the Q4 value? Is 6 times 7 minus 1. So as we said the other time, maybe the answer to the universe and everything within 42. So yeah, it seems that during this analysis phase, which is the let's say it's not the higher level of before of this higher synthesis of primality, but it is down to our level, let's say, of products and multiplication and all of this. So it seems we stop here. By the way, just to confirm, is that if we continue, we got the next p-value, that is P4, we will see that it's not part of the monster. So 43 does not belong here. So something we are getting right here. Okay, it seems that as if this symmetry indeed breaks there at that point. And this completes, let's say, the second step. And our last step, that is our last 2 steps before the end. It's step
Haris, could we go back up again to the first list of the monster numbers? You see here, when you went through, you showed how 6 times 2 is 12, minus 1 is 11, plus 1 is 13. 6 times 3 is 18, minus 1 plus 1 is 19. But then these 2 numbers are missing. The 23 and 29.
Here it is.
Are missing in the chart down below. Is there a reason for that?
My chart, you mean?
Yeah,
no,
down here.
It's everything here. 23 is here. It's an M value, 23. it's more prime, let's say, than it has more gravitas than the M values, the values that came from the first stage of synthesis. They seems to have more gravitas than the values that follow, that they are normal Q and P's. So this is M6 and this is M7.
Okay.
Okay. So now, as I told you before, if we took the output M tape with of the first step of the first stage, this one, and we folded it in half, we were gonna see that the fold takes place, as I told you before, between 7 and 17. And at this point, what we can do in order to find the last two values, let's say that complete the order of the monster, we can go back to our initial sequence, our starting sequence, A002822, and inspect if there are some non-prime values in between that space. And indeed, we have two prime values there between 7 and 17. It's 10 and 12. So what we are doing is we're gonna take, as we took in this case of M4, that we just took the Q, we're gonna repeat the same insights that we had from the previous stage of the analysis into the final stage of this integration. And we're gonna just discard the P's. We're just gonna keep the Q's. So it's gonna be 6 times 10 minus 1 is 59. And 6 times 12 minus 1 is 71.
So I don't understand where you got the 10 and the 12, because those aren't prime numbers, right?
Okay, I will show you. Okay, so it doesn't mean that the M values that correspond to this twin primality, twin pair primality, it doesn't mean that it's only primes. It's just something that I did, that I thought to do. Like the normal order is this.
I got it. I remember now. So you multiply,
Yeah.
anytime you multiply those numbers, you're going to get 6m minus 1, 6m plus 1 are going to be twin primes.
So for example, the first value that is not prime, because 1 is not prime, still give us two prime numbers, 5 and 7, right? But because it is not our table here, it's a triple basically. It's M, comma Q, comma P. So we need to, in order to accept a table, we need to have all three prime values. It's a table of primality, let's say. In this case, if let's say, for example, if the M value is not prime, but the two subsequent Q and P's are prime, still it's not, we're not gonna accept that one. We just accept triplets of primes. So in this way, when you get this 10 value, again, we didn't got this one from our initial primality sieve during the step of this higher primality synthesis out of this sequence, but we can go back and realize that, okay, is there anything between 7 and 17? And the truth is, the truth of the matter is that it is. So these are the two last values. So it almost completes the order of the minimal order of the monster, because there is one last final step 17, and this step is to remove any duplicates. In this case, we have the M4 equals, no, sorry, Q2 equals M5. So what we can do, and I had a little bit of discussion with myself, which ones should I remove first, and which should I keep? Because one of these, this is what I told you the other time, that this is a particularly fine distinction, because the one is super singular, belonging to the master, but the other is not. And why? Because here you can see, even if we go into the full order of the master, we can see that this 70 is singular. So it's not, we cannot accept the second one. And what I believe is true to do here is to give primacy during the first stage of this synthesis. So what we can remove is the Q value, the Q number 2. And actually this is our M. And we have a nice, let's say, pictorial description of this table, so we can present it, represent it. And this completes the construction of the master, the minimal order of the master group. Now, if you allow me, I can continue a bit further.
Yes,
and
please.
Yes, and I can use this methodology to also reconstruct the baby master. Okay, the baby master is the second largest of the sporadic groups, and it's called B, not M in this case. Now, a small note here is that, yeah, this is some notes that I have. So in the case of the master, parsing takes parsing. What I mean parsing? The parsing of our total Turing machine and of our analysis, basically. So of our analysis. So parsing takes place in this manner. It's Q times P, and then we discover what N is. Because we start from the M value, first we discover this Q, then we discover the next P, and then it's the N. In this case, of course, it breaks, but okay. It's important to also notice that we can represent this N value in each, let's say, for example, Q can be written as N times N divided by P. And of course, P can be written as N divided by Q. And when multiplied together, they give us N. Now, moreover, concerning the master group, symmetry breaks. As we said during the previous step, right here, after 2 times 3 times 5 times 7, which this happens to be the 4 primordial, which is important for the sieves of prime numbers. Now, let's repeat the same thing. And okay, I will come back here later. Now, okay, now the total number of the super singular terms of the baby master is 11. Right here. So the minimal order that we're going to take the minimal order, no need to deal with the exponents. It's this one. It represents from 11 super singular terms. So since we have 11, we can apply this small metric that I use, that again is the floor function of the total size, that is 11 divided by 2. In this case, it's 5. So we can expect to analyze only 5 values during the step of our analysis, and not 7 as before. So, and also, this is the second metric that counts the total number of steps needed to reconstruct the minimal order of, this is mistake, the minimal order of the baby master. It's gonna be the size plus 2, so we can expect to complete our algorithm in 13 steps. Now, again, we can have this distinction as before. We can group the first 12 steps as one, and we can leave the last one for the end. So again, here, what happens? Basically, we can construct the baby out of the M tape of the master. So we don't need to go and recreate to run our Turing machine again. What we can do is we can repeat this step. So we get again the first 7 M values, again up to 47. And then what we can, because as you see all of these numbers in this way, in this manner, basically we got these difficult numbers, 23, these difficult values, 23 and 47. So we have the M tape, and then what we are doing is the following. We expect to perform our analysis, as I told you before, only on 5, because that's the floor function of half of the size of the M of the size of the baby. And this time the important thing is this: as opposed to the previous time with the master that we were parsing during our analysis as Q times P equals N, here what happens is that we are parsing the opposite way. So, sorry. So it's gonna be P times Q equals N. And respectively, we can rewrite it like that. And let's go and check it out. So we take the first value is 2. Again, we do the same. Here we are going to report the p-value now. So it's going to be 6 times 2 plus 1. We note down 13. 6 times 2 minus 1 is 11. We proceed to the analysis of the second m value, that is 3. 6 times 3 plus 1 is 19. 6 times 3 minus 1 is 17. We can proceed to the next one, that is 5. 6 times 5 is 31. And symmetry breaks right here after this value. Why? Because the size is 11 and the floor of half of that is only 5. So again, during as before, the final step that finalizes, let's say, the reconstruction of the baby group, and that means that there is no need for total integration for the baby. That is applicable only to the master. So again, what we are doing, we are removing this excess duplicate value of 17. And what it means that we can write it down in this manner. So what I wanted to note, yes. So as I told you before, I mentioned that concerning the master group, symmetry breaks after the fourth primordial, that is 2 times 3 times 5 times 7, that equals 210. Concerning the baby group now, symmetry breaks after the third primordial, which is only 2, 3, 5, that is 30. And in this way, we can, let's say, represent the two. And this is the punchline. That is why higher synthesis comes before any analysis, as it represents the core of both of our constructions. So yeah, tell me if you have any questions or anything that you want me to clarify. I will be happily do that.
Well, I have so many questions because, I mean, I'm not a mathematician, so there's a lot of this that is a little hard for me to grok, but is this like step 1 of the proof now? Is that how that works, or is this the whole thing?
This is the whole thing, but this is the proof of the theorem, and the theorem just says that the structure claiming ownership, the structure claiming ownership of the master group is the structure N that corresponds to the prime M values of twin prime pair primality, and thus the twin prime conjecture. So even though that we did not prove yet that twin primality, twin pair primality is infinite, still it doesn't matter, because what we are trying to do is we are trying to reconstruct a finite sequence, that is the master and the baby. So two finite sequences out of an infinite sequence, because as I told you here, these values, they do not stop there. They go on and on and on and on and on. So in theory, if we leave our Turing machine running, and if we did not apply, let's say, this condition that you have to hold when you move beyond this upper limit that is 71. Let's say if we remove that constraint, we are gonna get a lot of continuation. Like if we simulate this, it will not stop. It will just keep going on forever and reporting M values that they correspond to twin prime pairs. Even though we don't know that is infinite yet. Simulation, let's say, results indicate strongly towards that case.
Okay, so if you kept going with this beyond you divided it in half and just worked with half of it.
Yeah.
And then you discovered that you can't actually go any farther than that without breaking symmetry. So it was right to break it in half and work with just the half right there. Okay, so and both the monster group and the baby monster group have this same aspect to them.
Yeah.
And you're saying that the twin primality concept is the world that these monster groups arise from?
Yeah, basically what I told you before, like this spillover effect that I talked before. Basically, if we take it to the next level and just make let's say the presupposition that indeed twin primality goes on and on and on, that means that the difference between the two prime values of each twin prime pair is equals to the even constant, and that even constant is 2. And then, as I tried to explain in the previous video, this allows us to even visualize what is happening. Like this process for me, it actually corresponds to what happened after the Big Bang. This is how I understand it, to be honest. And each m value, like for example, okay, what happened when, let's say, time was 2? Because all of these, you can understand that as emergent properties. So we discover both space and time because we observe that. If we were not observing, we will never know. So time is entropic because it's the difference between the two different m values. Like for example, between 2 and 3, we can see that we have different n1 and n2. So one is 323 and the other was 143. There is a difference there. There is a difference there. But what does it mean in reality? Okay, I can allow me to show you this one. So this is one of the Platonic solids. One of the 5 Platonic solids is the octahedron. So the octahedron, of course, it has the same height and depth, and it has a particular, let's say, volume, right? What we can do, what I suggest is that when we weight this one, and when we weight also a slightly jaded version of this solid, let's say a hidden solid, I don't know, maybe Plato missed this one. It seems that it's gonna weight exactly the same. So because two different solids weight exactly the same, there must be a connection and much deeper connection there. So instead of having this height as 6m and this depth as 6m, and in total that means 12m, and when, for example, 12m, let's say the m value is 5, then 12 times 5 is 60. So what I say is like, okay, I can recreate another solid that is not an octahedron but looks like this. And instead of using 6m and 6m, so 30 and 30, I can use P and Q. So I can use 31 as P and 29 as Q. So I'm using the pairs of the twin prime numbers in order to reconstruct something that is similar with this, but it's not exactly like that. So how I came up to discover, let's say, or stumble upon this, because I surely didn't invent it, it was there. But what I thought was like, okay, what will happen if we take two opposing rectangular pyramids and stack them up together? We're gonna get something that looks a bit like this. So let me actually go here and start by showing you all the different work that I have done, and I prepared to show you. So this is the M value. I believe that slowly things will start making sense. So if I want to calculate the volume of this solid, or of the slightly different version that is equal to this, the formula that I can use, given that I accept that the difference between the two is always constant and is C, actually can be written by this formula right here. So these are different formulations of the same formula. So for the volume. So in this theory, let's say, the volume, it equals energy times N, where N, of course, is the length. Now, what is energy? Energy, in this case, in Einsteinian case, it's mc squared. But in our case, in our interpretation, let's say, we accept that the speed of light has a slower limit, that is 2. So we use that slower limit. And if you ask me, that slower limit actually give us maximal entropy, which goes back to the twin prime pairs, because it's actually the most difficult case to discover a twin prime pair as compared to everything else, because it's like rather exceptional and unique. So if we accept this interpretation, where C equals 2, that means that energy equals to 4 times M, or P plus Q, to talk with prime pair terms, divided by 3. And equally, it's equal to the volume divided by N. Now, this is actually rather interesting, because this formulation for energy arises out of the energy of the photon, that is E equals h times frequency, which is the constant, times the frequency. And we can define this constant at a later stage. So the two M values cancel out and they give us this term. So let's make some examples. For example, let's take the case where, that I said before, the M value is 5, and that means that Q is 29 and P is 31, and equally the 12 times M equals to 60, which is P plus Q, 29 plus 31. So what do we say here? That we're gonna try to calculate the volume of our jaded solid. Actually, what we are doing is 4 times the M value times the N value. So to write it down, it's clearly not possible, sorry. So it's 4 times 5 times N, and N can be written as Q times P, which is this number here. And you can see in the factorization that actually it's 4 times M times N, which is Q times P. Now, if I want to choose, for example, an even higher value of M, let's say, for example, 17, what I can do, and there is a formula for calculating N. So for example, let's use that one now. This formula goes like this: 36 times 36M squared minus 1. And this actually comes from where? From 6 times N minus 1 times 6 times N plus 1. So you get this formula for N. N is this. So let's go and try it now. 36 times 17 squared minus 1. What does it give us along? What does it give us a C? So this is our n, which is 101 and 103. That's a prime pair. And this is the volume of that solid, of that rectangular jaded octahedron, let's say. And again, it's 4 times m, so it's m c squared times q times p. Okay. What can do now? Let me get back
So
here.
what you're doing here then is using this theory as a way of going beyond just the monster group and using it for calculating other.
Other solids or even other quantities or formulas. So, for example, let's see, and it can go even beyond because this is like standard geometry. So what I can do is that I can define, because it's appropriate to define things, and this is also very interesting concerning the Oliver Sacks video from Paul van der Klee. By the way. Okay, so okay, I will make the link in a bit about that. So what we can say here is that as we defined E, that is MC squared, or in all these different interpretations, let's say that they are equal, we can also define T. And T, in this case, instead of being 4m, T, let's say we define it to be 3 times m. This will become apparent in a while.
So is that just an arbitrary choice?
No. This is like, for me, 3 represents the Trinity. It's like it's embedded there in the fabric of the universe, let's say. So this is very, very fundamental for me. Yeah.
And you're using T to represent time.
Yeah. It's okay. And maybe if somebody comes up with something better, let's say, but this is the nomenclature that I gave to it in order to be as as clear as possible. So in this way, what we can do now, we can also define T times E, and because T is 3m and E is 4m, that means that T, which is what I refer to as truth internal, actually this is equal to 12 times m squared. And for example, going back to the m value of 5, we can see that it's a very nice round number, that is 300. So 12 times 25 is 300. And this is how we calculate that particular thing. But why is this important? It's important because what I want to get here is this one. And this one, it's 12 times m squared times n. So it's T times n, or 10. You can write it as 10 as well. So let me write it here as 10. So now, what is this T? Let's say, let me call it true volume for now, just to make sense. So this is the volume of this solid, which for me is the fine essence of the thing. And this is this formula right here, where we multiply T times V, actually represents it's a bit strange to put words into this, but this actually represents a prism. Okay, that is a rectangular prism that is 12 times m squared times n. So it's like a big rectangular prism. And what we're gonna do, we're gonna calculate the volume of that prism. And this prism, actually, it's first of all can be calculated by this formula that uses only the m values. Just to make a quick demonstration. Okay, so for example, let's go back to the value of 5. So this is the total volume of the prism that represents the m value 5. And just to be correct here, sorry, I'm also gonna write down the M formula for the calculation of the initial volume, the V, which is this one. So we have these values. Now, do you see how close these things are? Actually, one can be embedded into the other. So what it means that this prism that we call TV is comprised from 3M times V. So if I come here and I just take this V value and I multiply it by T, by T, that is 3 times M, or 3 times 5 in this case, I can expect to find exactly the same value. This is it. So it's not only it's not only this shape here, but we start from this shape that is like the fine essence, let's say, of the thing that were investigated, that is primality and two-prime pair primality and the master. But we can actually get into this total volume, or the whole volume of the, how to put it into words, let's say at time M equals 2, the total volume of the universe back then, let's say, was this 68, 64. At time 3, it was this value, 34,844, and it goes on, it continues. Of course, we stop here, but as I told you, we don't need to stop here. We can continue up to this day, from the Big Bang all the way up to this day. Now, why I keep on calling this like Big Bang and all of this, I will show you.
Well, so one implication that would come out of that, if this is theoretically correct, is that this would explain the expansion, the continuing expansion of the universe, because
this is a continuing expansion.
Yeah.
But what I want to show you is that basically I did something that Riemann did, not in his great way, but I just got inspired by his analytical continuation. Okay, and what I did, I went back, what happened before? You know, if this is true, I want to know what happened. Like, right, everyone knows what happened up to a particular, let's say, a small fraction of the milliseconds. Let's go back. Let's go even before. So the volume before actually is going to be 1, right? What happened at when M was 1? And we can get, or even before. So I created this. I'm going to show you what this is. So when the M value was 1, the total volume was 420. Okay, and just contrast it with this one. When it was 2, it was 6,864. So it actually goes up. It doesn't explode, but it goes radically, let's say, exponentially upwards. And when it was, this is the cool part. Because I believe in the trinity to the value of these 3, I believe personally that the correct way to parse what happened between 1 and 0 is to try to calculate what happened at the 2/3 of M, or 2/3 of 1, let's say, and 1/3. So if we go on 2/3, we discover that the total volume was 80. So from 420, it went down to 80. And when it was just 1/3 of the millisecond, let's say, the volume was 4. So this is how it went up. It went from 4 to 80 to 420 to 684, and goes on and on and on and on and on. It continues. So what happened when the M value was 0? Well, you can see a lot of zeros here, but the important thing is this one. do you remember the formula that I told you before for n? This actually gives me allows me to make the following calibration. Now, allow me to start from here. Okay, so yes. 143 was 11 times 13. Okay. 35 is 5 times 7. 15 is 3 times 5. Now we're going down to the prime numbers. This is the natural order of the prime numbers. What happened if what happens even before? 3 equals 1 times 3. And here comes the good part. It was like this. It was minus 1 times 1. So the n value was actually minus 1. It wasn't like 2 or something else. It was minus 1. So this negative here is very interesting because it allows us to think that maybe negative entropy exists. And I can even, let's say, imagine like what happened even before. So, okay, we went down from 2 to 1 to 2/3 to 1/3 to 0. Is there a way to go before? So one might ask like, okay, then you can go to minus 1/3, right? Well, that doesn't really work. Why? Because when you do, for example, sorry. Yeah, it doesn't work for the following reason. Imagine I'm putting here, sorry. Instead of 5, I'm putting minus 5. Okay. So I'm putting a negative m value right here. It doesn't change anything. So it means that this thing is true regardless of the minus or plus sign. So even if I got like a negative value, because the formula that we are using is m squared, minus 1 will become 1, right? It will not, minus 3 will become 9. It will not stay negative. So there is no way to, it seems that there is no way to go to what happened before them values existed. So there is one way, and that way is to assign to the m value the imaginary unit. So if we assign the imaginary unit to this formula, interesting things appear. For example, the volume, the energy in this case is 4I, is not 4m, but 4I. T is equal to 3I. The volume, which it's very strange because this is Q is 6I minus 1, and P is 6 times plus 1. So the value of n here is actually minus 37. Why? Because it's 36 times I squared minus 1. I squared is negative, so we have minus 36 minus 1. So we get that when the m value is I, the n is negative, and specifically it's minus 37, which is very paradoxical to find a number there. For example, the volume of that solid, which we cannot even imagine because we are talking about imaginary units, it's minus 148I. That we cannot parse, let's say that something like that. But what we can do is we can calculate the total volume by using this nice formula here. So when we do, for example, 432 times I to the fourth power minus t, which is 12 times I squared, we get 444. And it's very strange that we get this number. Very, very strange. Why? Because when m was 1, this total volume is equal to 420. But when it's the imaginary unit, is equal to 444, which is very strange, because if we know that we know from our mathematics, let's say, that I squared, I squared equals -1. But we have just shown before that if we take the m value equal to -1, we will arrive to this volume. But the right answer is this one for the imaginary unit, is not this one. So again, I believe this is something that was hidden, and now suddenly it's getting revealed by the light coming out of moonshine theory, which again is paradoxical because we're talking about light coming out from this crazy moonshine theory. So this is what I believe. It's important to share with the world, and this is why I contacted you. These results, as far as I am concerned, they are valid. I've triple checked them many times, and I got some feedback from people that I know, but I want to reach out to others in order to, if they are willing to falsify, let's say, my theory, they have everything to perform that. But I am almost certain, if I can say that this is indeed is true. Like it's something that was somehow hidden and somehow, I don't know, by the grace of the Lord, I managed to look at it, to have this small glimpse on it.
Well, okay, so the original basis of the theory you said is that there's a connection between the twin primality and the monster group. Is that something that no one else has seen before, that connection?
Yeah, I believe no one has seen. Actually, there is one bottle of whiskey to anyone that answers that question, so I want to claim that bottle of whiskey.
And then once you kind of wrapped your head around that there is a connection between the twin primality and the monster group, then how did you get from there to this analytic continuation?
It's because when I started thinking about the volumes and the solids, because I said, okay, if there is something like I can represent as a solid, then it means I can calculate and weight. So
hold on a second. So what are you so how did you get to this idea of the solid? Were you thinking that the monster group has something to do with the Platonic solids?
No, the only thing is because when I went, it's like a small connection. I thought, like when I visited Egypt, like back in 2005, something, I've noticed that the pyramids were shaped like this. They were not like trigonometric or, they were not a tetrahedron. They were like an octahedron. So when I went, when I started looking into the master and all of this, and made this connection with the pyramid structure, I said, is it possible that nobody figured out that there is this type of solid? And I started looking at it, and I realized that people, they are talking about regular pyramids, that they are not square, because the pyramids, they are square, right? This is not square, this is rectangular. So people, they were recognizing these regular pyramids, but nobody made the connection that you can take two different, stack them out together and emulate like something like that looks like an octahedron. And the only thing that I thought that make the connection was like, I was certain that when the Egyptians built the pyramids, they were not square. Like even for a fraction, I am certain that they couldn't make it exactly square, right? Because there is human error involved and all of this. So I believe this is, let's say, the hidden variable that I've noticed. And everything followed up from there. Like I thought, okay, if this is V, then it means that this can be embedded into a hyperspace, right? And this hyperspace, why not represent, let's say, the hypothetical full volume of the universe during that time? And it allowed me to start thinking about this. So what I told you before, like if I take this V value, that is this one, so this is for negative. Yeah. So if I take this value and I multiply it by times doing a mistake here. So it means that it can be rewritten in this sense that like m times p plus q times n. And it's gonna be exactly the same volume of that prism again. So there are many different ways to reformulate that calculation. And it's like that, like you can imagine different formations that they all work and they all are valid and weight the same. That's the fundamental distinction. And for example, if I get this number here, I can write it as n squared, sorry, n times n plus 1 divided by 3. Okay, so let's say for m value equal to 5, that means that n is 899. So when I do the normal type for calculating the volume of that prism, I get this value here. And when I do it with my way, I get it exactly the same. So it's like this. Yeah.
So do you think there's something special about that number?
Yes, and I can now make you give me a great pass to make the link with Oliver Sacks and the twins.
Oh, okay.
Okay, so, this, as I told you before, that this is the total volume, right? This is the formula using only m values to calculate it, this is the difficult part, to be honest. So actually, what happened with the twins, what I believe they saw in a flash, and it's interesting that Oliver Sacks uses, they saw in a flash of what? A flash of light, probably, right?
Mm-hmm.
A flash of light from their internal eye of I don't know how they managed to do it. It's still it's a let's say paradoxical or even a miracle that they were able to perform this. But they managed to see it as concretely. You understand? They managed to see it as 37, 37, 37. They did the partition into 3 like single-handedly in their together in their mind. What I can do is I can offer the abstract, let's say, calculation for what they did. So first of all, you remember Wheeler's it for bit, right?
Mm-hmm.
Okay, so what we can imagine, if you allow me, is instead of getting it for bit, we can move beyond and get for it out of it. We can call this it what the what the twins saw. That is the interesting, let's say, thing. And just to play a bit with words, I can take this for it, and I can subtract 432 I to the fourth power divided by 4 times I squared, and I can get the exactly same number. So just to explain what I did here, I took the volume, this formula from M, I replace it with the imaginary unit, because when we say imaginary unit, it's something that doesn't exist in this space time, let's say, something that it's outside in a way, let's say, of our M value system. So I exchange it with I, so it became 432. Let me just make the calculation here. Okay, so it's 432 times I to the fourth minus 12 times I squared. Sorry, I put one there. I. And we get this number 444. Okay, and what is this 444? When you divide this by minus 4 times I squared, we get the 111 that they saw. So this is what I believe they saw in a flash. Now, what I find really interesting here is that this 111 that they saw, in fact, is not 3 times 37. It's minus 3 times minus 37. So it's this value that we have here for the I, or the imaginary unit. You see, the N value is minus 37. So what they saw there, I think, is way beyond what is fundamental to us. Like this is, for me, that is the core of what is fundamental, is what exists in a way outside of 3D space. So yeah, this is what I wanted to share with you. I don't know if
it almost sounds as though you feel like you're able to calculate the there's no good word for it. Imaginary is not the right word, but but that world of mathematics that lives, that exists, that we sometimes manipulate it, but there's so much more there to find. Because it's there, it's actually there. I have one mathematician friend who says that when he starts doing mathematics, he is walking through an actual world of numbers. He's there, in there with all the numbers and all the beautiful shapes and everything.
It's like a castle, let's say. And you can stroll there and see and view all of these things. This is how I imagine, like, for example, when we say they discover these Platonic solids, or they discover these new solids that they come up during 2022, like the amplitude dihedron, how it is called. All of this, I believe they exist, but it's very difficult for us to grasp. But in this way, as you said before, imaginary is not a good word. Maybe they manage to perceive with their inner vision. I don't know how to call it, because in a way, this trick that I did here. It's interesting, because when you go to the negatives, or when you change the pole and you go to the imaginary unit, what you can do is that you can flip the components of the equation in order to arrive to the truth. So you can just put what I have written down here like this, it can be written with this minus I here. But in this way, it's I think it's more appropriate to visualize it like this. This is what I believe they were able to see. It's unbelievable that they managed to perform this calculation, but because they are coming from this side, from the side of the concrete, and this value here is like, for me, it's exceptional that it happens so to be that value. It's like it's beyond my comprehension. This is the best thing I could come up with as an explanation, let's say. Okay.
So at the expense of, I know this is a really lame question, but remind me again what that n represents.
What that? Tell me again.
The n, this one
Then
right here.
P
Yeah.
times Q. P
And
times N equals P times Q.
P
So,
times Q.
yeah.
So could we go back up and look at the tables again where P and Q show up so I can just solidify it in my mind?
Here it is.
So the P times Q has to do again with the 6 times m minus 1, 6 times m plus 1 thing with all those m numbers.
Yeah, and exactly, we just make this, instead of putting a numeric value, an integer value for m, we use the imaginary unit. And we get to do this for all the different formula. Like, for example, we can understand that P plus Q is this one, is 6i minus 1 plus 6i plus 1. So the two ones cancel out, and we just have 12i. And when you when you actually want to calculate this TE value, we get again this negative number, minus 12, which is also important and interesting in mathematics. It's to be found in many sequences that have to do with summations and all of that. So these numbers, they are very, very interesting. And I believe not only for me, also for even a mathematician, and not only a number theorist, let's say, from other fields of mathematics. When they look at this, I believe they will also see some value. Okay, it has to do with values, but okay.
Okay, and then once more, this T here that goes with this E is energy, right?
Mm-hmm.
And that T, in your previous chart, you were talking about time when you showed T. Is that the same T?
Yeah.
Okay.
But it's just a different, let's say, perception of time. In this perception, time is always a multiple of 3. So we get the m value, and because time is 3 times that. So it becomes relative with each different m value choice. So if it's gonna be 103, the m value is gonna be 309. And if it's gonna be the imaginary unit, then t is gonna be 3i.
Okay, so could we work backwards on that and ask you, at what Einstein calculated the speed of light, what would T be?
Okay. So energy was, wait.
I guess what I'm asking is, what would the m value be for the speed of light based on this chart?
The m value for the speed of light. Okay, I can tell you what is the m value for the monster. Now, if you want, it's 231. And wait a second. Actually, it's, if I'm not mistaken. No. Wait. Wrong. No, just give me a quick second.
Well, I don't even know if my question makes sense, but I just had a
No,
thought.
no, it's fine. It's fine. It's fine. It's your question is very difficult. I tried to answer it, but and I will explain to you why it's difficult because the full speed of light it breaks at 4, so it's fourfold. It's the maximum complexity you can I can imagine. Let's say the master it breaks at 3, so I can tackle that. And how I can let me just. Okay, so what I told you before, that the M value for the master is 231. Yeah, and actually can be written like this. If we allow, because this 71 is important. Okay, so allow me to call it Q. It will become apparent because it's also important in terms of calculating the speed of light. For example, I can calculate the speed of light just by writing it like this, PC, 511 PC. This is how I see it. And why? Because 511 is 2 times 73, right? Sorry, apologies. 511 PC. Okay, so it's, yes, it's 7 times 73. That is the 511 part. P is the large prime that belongs to the light, the speed of light, which is this one. And in our, let's say, worldview, in my worldview, the speed of light is the slower limit, so it's 2. So this is the speed of light. Yeah. And what I can do, you see, here we have this 73 that belongs to the speed of light here. For me, this 73 can be written as Q plus C. It's 71 plus 2. And this is why I can formulate the master, at least in its, the master's minimal faithful representation, as we said the last time, is 196,883. Okay, so when we calculate 12 times 231, which is the M square value. So what we are doing here is that I had calculated the M square value being equal to 231, which is very, very, very unique because it's not easy to get it. What you have to imagine is to imagine like the M value is equal to the square root of 231. And 231 by itself is interesting because it's 3 times 7 times 11. Again, all these numbers, they are also part of the master group, so they have some interest also to that. So when we calculate 12 times this value of M for the master, let's say, we get 2,772, which is interesting because it's one less than M5 times it's M7 times Q5, which is 47 times 59, which is the 2 of the largest super singular terms of the prime other than 71. So yeah, we can represent it also in this term. And we can even move beyond now to what was your question again? Now that we have some background, it was concerning the speed of light, and you asked me about the M value.
Well, we would have to go back to the graph that had the T on it.
Yeah, this one, right? Or the other.
Yeah, so you were looking at, you said T, which represents time.
Time or something else. Let's say time. Yeah.
And that M represents it changes based up here, right? So M is this variable. And so you're saying that this T changes based on whatever 3 times that variable is.
Yeah.
I'm having a hard time getting a grip on what this is that I'm looking at.
With the T. The T basically is a definition. It's not like something that got out of something. For example, in the case that I told you, yeah. So let me go back to energy for a second. Just maybe it's gonna be helpful. But so in the case of Einstein, it was energy is equal to mc squared, but also it can be written as energy equals h times frequency, right? So of course h it's now we're talking about the energy of the photon, but here in this case our constant is not Planck's constant, which is very, very small, because we are talking about prime numbers and all of that. I had to redefine it in this way. So h, this constant, it's going to be equal to v divided by the m value. Okay, and the frequency, respectively, it's going to be the m value divided by n. So when I multiply these two together, I'm gonna get V divided by N. V is this volume. V is this volume here. So imagine if we calculate it, when we weight this volume and we divide it by N, which is P times Q, we're gonna get the energy. Now let's practice what we say. Okay. Now E equals H times F. So H equals V divided by N, and F equals M divided by N. So let's calculate H first. So V equals, I'm going to use the short formula. It's this one here. So V equals 4 times, for example, 5, where the N is 899 because it's 29 times 31. Sorry. This is, okay, again, equal to this, 17,980. That's our V. So we're gonna divide this value, by N in order to discover, let's say, H by M and divided by M. So it's gonna be, it's gonna be this value here, which is 4N. Okay, so in our case, the constant of H is equal to 4N, 4 times N. Now, regarding frequency is M, that is 5 divided by N, which is 899. Allow me to perform this calculation on right here because, okay, so it's a very small number. But when we multiply the two together, H and F, we get the energy, which energy is mc square. It's 4m, so it's 4 times 5 is 20. So this is like a link between I don't know, my calculations and I don't know, quantum mechanics or something like this, because this has to do with frequency and the H value, H constant. The same thing we can do for every other value of m, either from here or from the other table or any other prime value. So this T for me, yeah, it's important. I'm gonna think about what you said and I'm gonna come back to you, like to try to calculate it for the speed of light, that T.
Well, yeah, I would at least like to know what the relationship is between T and the speed of light.
Okay, I will take a note and I will answer
Because,
to you.
I mean, because when you're talking about volume, in a sense, you're talking about space, right?
Uh-huh.
And then you're talking about time here. And so you have space, time, you have space and time. And you're able to do certain calculations regarding space and time with this.
Yeah, for example, let me just give you one example. I will take this case, the most extreme case where m equals the imaginary unit. When m equals I, as we've seen before, the total volume or the TV or whatever, how we call it, is equal to 444. Okay, this can actually be translated into distance. We can understand it as distance. And okay, this is just one example, but what does it mean? Okay, so Bernardo Kastrup always talks about the Pleiades, frequently talks about the Pleiades, just to say, yeah, maybe someone is broadcasting from there. I don't know. So you see, I'm using this example because it's a nice coincidence. The distance from the Pleiades star cluster, which is called the Seven Sisters, to Earth is equal to 444 light years. So we can make the calculations. Unfortunately, I don't have them with me, but I did the calculations. We can make the conversion from light years to miles, and then we can extract this distance from Earth to the Pleiades in the exact same manner. So we can calculate this via the m square value. So this m value is important because it allows us to represent distances in different way. So this is something.
So basically what you think you have found, you know how Stephen Wolfram is always talking about how the whole universe is mostly computationally irreducible, but there are certain slices of computational reducibility within the universe. And those slices of computational reducibility appear to us as observers because of the kind of observers that we are. So because of the kind of observer that you are, you have found a particular slice of computational reducibility that allows you to use this method of computation to determine a lot of other frameworks that exist in the mathematical universe. Would that be a good way to summarize it?
Yeah. That's a very good way to summarize it. And I believe let's say, for example, with this framework that I am presenting here, that arises out of this proof for the connection between the master group and the structure that belongs to it, which is the twin primality, we can find some similarities, let's say. And one of the similarities, you remember in our initial construction, we were talking about this 42 that breaks here, right? So it's interesting that when the M value is equal to 1, the total volume is equal to 420. And that the difference between the total volume when M value is equal to 1 and when the total volume is equal to I, it's 24, which is interesting because in our human standard terms, it's 24. So maybe it's 24 hours. I don't know the difference. Like because now we are imagining what happened even before the Big Bang. That for me, that's like a huge revelation. Let's say that I am able to present and make such claims, or even go back and think of what happened in different fractions of right after the Big Bang, or even before. That's the main gist of the matter, let's say. And one way, just to add something to what you said before, I believe that what Wolfram says is correct, and the reason that we are able to glimpse these small facets of truth, let's say, is because of the measurement problem. At some particular values, the measurement problem is not a problem anymore. So at these values, this measurement problem goes away. And I can actually use, if you have time, I can show you how I can distinguish between real numbers. Like for me, not all real numbers are real. And because a real number,
I would love to do that next time.
okay.
Let's make that a plan that you're going to show me how to distinguish between the real numbers.
Yeah. I have a construction based on the master of the minimal faithful representation of the master, let's say, and I'm using that to reconstruct the master. I'm gonna give you just like a small a sneak peek, just to understand.
The other thing I would like to talk about next time is, rather than trying to do so much math, maybe next time we could talk about the implications of this in what it means to you personally and how you see it in terms of maybe philosophy of science or the philosophy of math or something like that, in terms of your own way of thinking about it.
Okay. I will happily share that with you.
Okay, so now we're doing a calculation.
Yeah, just a quick second. Okay, so you remember in the previous talk, I told you about a short theorem from McKay that was can be written as m plus 1 equals 196,884. So it's the master, the minimal representation of the master, that is the three largest prime numbers, 47 times 59 times 71, plus 1. So I've discovered a way to represent this m plus 1, let's say, in a different manner. And this manner has to do with something that it's even more crazy because it has to do with a probable transcendental number. And in this case, our transcendental number is p to the power of p. So what I'm doing here, I'm pushing my own theory to its limits and beyond. And I'm saying this m squared, what will happen if it's equal to p to the square power of p? And I'm times 12. And I am using that in order to define a value that I call psi from the Greek letter psi. And when I divide that by 12 times p to the pi, I get as an answer the back m+1, which is this number. So it's also interesting. I think I will be delighted to show you. I also had prepared some things regarding some work we did some years ago with fuzzy cognitive maps, particularly in the capital city of Croatia, Zagreb, regarding green park design for where the National Autistic Center was based. And it was a very difficult problem because they came to us and they told us we have this space and we want to create a park that can be used by the children with autism that they live in the center. So when their parents come from another city, let's say from the far country, from the countryside, they can take their children to go there and spend some time with them in order to see the children. But they told us that we want this design in a way that can also satisfy the needs of non-autistic kids and their parents that they live in the neighborhood nearby. So it was a very unique problem, how we utilize space in order to accommodate the needs of two different categories of people and their parents. In one case, autistic kids were their carriers, and in the others, kids with, let's say, normal kids without any developmental problems, along with their parents. So I will be also delighted to show you some of
Yes,
this.
that'll be really good. So let's think on those things then for the next time we get together, and I'll get in touch with you by email to set up a time.
Okay, and I will try to take into account your questions and your feedback, which is it's great. It's great. And sorry for giving a lot of mathematics. I hope it was a bit clearer this time. And
It was, and I'm hoping that the mathematicians that are watching can maybe parse it out even more and come up with some questions for you.
that would be great. That would be great.
Because I can't really ask very intelligent questions because in a very deep sense, I don't understand the underlying theory. But
Okay.
but I can see what this could do if it's an eternal truth. I can definitely see what it can do. So
Okay, great.
oh,
Great.
this has been great. Thank you so much, Harry.
Okay.
Let me just bring us back. Oh, why don't you bring us back from share screen so we can say goodbye?
Yeah. So
Just hit stop share up at the top.
wait a second. Apologies.
Should be a red button at the top of your screen.
Yeah. Okay. Great. Okay.
Here we go.
Okay. So the last thing that I wanted to add is something that I read from a Japanese proverb. I think it's sometimes this folk wisdom has some truth in it also, and maybe that's why it got through the test of time. And it had to do with if you fell down 7 times, you stand up 8.
Yes, I learned that one when I lived in Japan.
Okay.
And I actually used that as the title of one of my paintings.
Wow, I didn't know about that.
But it's a very peculiar statement, right? Because if you fall down 7 times, you can only stand up 7 times.
Yes, but it presupposes that when you arrive at the scene, you stand up. So everybody's calculating, you fall once, you stand up once. You fall twice, you stand up twice. But actually, you have to think that, no, in the truth of the matter, we come into this world standing, so the last time we keep on standing. This is how I understand it. And it's interesting that it's, again, 7 times 8 is 15. So this is something else that I noticed. Small details that maybe is of interest to philosophical discussion, let's say.
Okay, sounds good. Well, we'll talk to you soon.
Great,
Thank
great.
you very
It was
much,
a great.
Haris.
Bye.
It's a
Bye. Bye.
delight talking to you again. Bye-bye.
Bye. Bye.